All right, so I posted this interpretation guide on Moodle, and I think you should be able to read through everything and learn what you need to. But I just want to make a quick video and give you some comments just to illustrate some things to hopefully make this guide a little more useful. In this video, I'm just going to do the first 8 because I just want to show you week 3 material. And then I'll make a separate video for 9, 10, 11, and 12 because that's week 4 material. So I just want to keep these things separate. But as hopefully you've seen by now, when we run a model in R, so if I say our classic housing data, price and square feet, and I want to check the model output using the summary command, I get all this stuff. And it's a lot of stuff. Some of it you need to look at, some of it you really don't. So I just want to, I wanted to help you pick through that a little bit. And again, you can read through all these things. I don't need to belabor all these points. But just to make a few comments, it will always give you the formula back, just so if you want to check that you ran the right thing, you can see that here, that it's showing you what you have run. It also gives you a 5-number summary of the residuals. I've never used this, but you're more than welcome to look at it. So it takes all the residuals and gives you minimum, median, etc. But the real heart of what you're going to look at and interpret is down in here. And that's what I have in this PowerPoint. So very briefly, let me just identify some of the things that we have in here, and then just make some other comments. So the model I have in this set of examples is with the NBA data, and I just did a simple linear regression using the number of games won as my response variable and points per game as my explanatory variable. So pretty straightforward. Here's the theoretical model. Great. So this first box shows us where our parameters are located. So it shows us that we have an intercept, which we will always have, unless we tell R to not have an intercept. We're not going to do anything with that in this class. We will always have an intercept value, and you never need to worry about taking that out. So that'll always be in there. And then any variables that you have in your model will be listed right here down below. In this case, since I just have 1, I just see points per game. The next column over gives us, this says estimate. And what this is saying, this is giving us our estimated coefficients here. So this column here gives us our betas. And these are the things you're going to interpret. So this first one here, this negative 194.5434, that is our intercept value. That is our beta 0, our estimated beta 0. And what does that mean? Well, just like any other intercept in an algebraic equation, it's the average value for y when x is 0. So what it's saying is, when points per game is 0, we would expect to win negative 194.5 games on average. As you can tell, that doesn't make a lot of sense. So as we've talked about, the intercept value, often we just don't interpret. We don't use it. It doesn't mean anything. It's just there. The next coefficient, 2.355, this corresponds to beta 1. This is really important. This is what gives us, in a sense, our practical significance. This shows us the numerical relationship that we see between our two variables. And what does this mean in general? Well, since it's a slope, what this means in general is that given a 1-unit increase in x, there will be an expected change in y on average of this amount of beta 1 units. And what this means in our case is that for a 1 point per game increase that our team scores, we expect them to win 2.355 more games in a season on average. So again, we're predicting the number of games won. On average, we predict averages, and this number here is considered with a 1 unit change in our X. You can look at other amounts of change, like a 10 points per game change, or a 100 point per game change, and then you have to multiply or divide your coefficient accordingly. But for our basic interpretation, it's just a 1 unit increase in points per game is associated with winning 2.355 more games on average. And you might notice that we can say this because we're dealing with two continuous variables. If we have categorical variables instead, the interpretation changes. We will get to that in later weeks. So for now, just keep this in mind that this is for two continuous variables. It's just interpreting how things move on that regression line that we've seen. So really, that's probably the trickiest thing to interpret from all this basic stuff. So let's just quick show you what these other parts are to wrap this up. So since we have an estimate for a coefficient, it has some errors attached to it. So this is a column of standard errors. And what this means is, remember what standard error is from the review sheet. It's the variability we would expect in the thing we're looking at if we did repeated sampling. So this captures sampling variability. So if we were to redo, like look at a different season other than the one that was used for this model, we might not get 2.355. We might get 3.1. We might get 1.8. That ability for this estimate to vary is captured by the standard error, and it's an estimate. So this is just an estimate of variability and is called a standard error. Right next to that, we have something that you've hopefully seen before in another way, but the t-score, the t-value. All the t-value is in a regression is just a ratio of the estimate divided by its standard error. So it's saying, how big is my estimate relative to its error? And the bigger the estimate is relative to its standard error, the bigger the t-score. And if you also remember your basic inferential statistics, a t-score comes with a p-value because a t-score falls on a distribution. And that's in the next column. So each of these t-scores has a p-value with it. This p-value, which has n-2 degrees of freedom, is just telling us how statistically significant each of our estimates is. Again, since we don't really care about the intercept much, we don't really worry about the p-value on the intercept. We care more about the p-value on our values down here, our variables down here. So this is really, really tiny, 1.98 times 10 to the negative 6th. So we would reject our null hypothesis and say, yeah, this 2.355 is statistically significant. So again, just a quick reference, this is assessing statistical significance. This 2.355, that's showing practical significance, because that's showing the actual value of the relationship between these things. And hopefully you've seen this in the other video and in the chapter, and you'll see it going forward, but the null hypothesis that we are rejecting in this case is that this estimate is equal to 0. But you will get more of that in the other content. And you'll see these little symbols out here. There's just a little significance code guide down here for what these p-values are associated with. So 3 stars appears to be the most significant. I don't really look at this because I can just look at the p-values and I know what they mean. But if you've got like 20 variables here, you can take a quick look for the different stars, the different symbols, and see what kind of significance you have. Lastly, for week 3 material, is this thing called the residual standard error. This thing has a lot of names, and it's really annoying. You may hear it called by different people and different textbooks the standard error of the model, the standard deviation of the residuals, the regression standard error, like it is here in R, the root mean square error, the RMSE, or as I like to think of it, just the typical error. What this is just a very basic quantification of how well or how poorly our model is doing at predicting the data on average. You can think of it like an average error for your model. So we know that sometimes our model predicts close to the data. Sometimes our model predicts really far away from the data. So on average, how good is our model doing? How well is our model doing? Excuse me. Now, there's a bunch of formulas and stuff down here. You'll see this in the videos a little bit. You won't ever have to calculate this by hand, but I just wanted you to see where the formula is coming from and what it is, and we'll talk about it elsewhere. But here it is. This is the notation that the book uses, so you might see it listed like that. But the residual standard error is this thing. It's the typical error of our model. So how might we interpret this in this case? What it's saying is that this model is off in predicting the number of games won on average by about 9. So it's about 9 games won off when it tries to predict the data. And, that's okay. But we want our residual standard error to be really small. We want our model to do a really good job of predicting. So this residual standard error is used in these other statistics below, but we'll pick that up in the second video of this and for week 4 material. But again, the residual standard error is sort of the average error of our model. And so this model, when it tries to use points per game to predict the number of games won, is off on an average of about 9 games. It either on average predicts 9 games too high or 9 games too low when predicting individual data points. So this is one way to quantify how well our model is doing. Great, so that's the first part, and we'll pick up the second part in the second video. Thanks.